Hello everyone. The work I'm going to present by myself and my PhD directors, Serguei and Alan Schmitt, is about abstract machines and more broadly about semantics of programming languages. But before I can get into this, I'll have to describe a bit skeletal semantics, the framework we are using. The point is to answer a very important question, which is how to define a programming language. The way we know to do this is to grab a piece of paper and write the syntax and semantics of our language. For call by value lambda calculus, you can say that the term is either a variable or an application or a function, and then describe the semantics either in plain text English or with inference rules. Like here, we can say that a function evaluates to a closure, and that if you want to evaluate an application, we evaluate both parts, extend the environment as usual, and compute the rest. This is a good first step, but nowadays you can go a bit further by putting your definition on a computer. This allows us to certify properties of our programming language and also develop tools like interpreters, debuggers, adapted to our language. You can do all of this in a proof assistant like Coq. It is doable, it has been done before, but you're a bit on your own. You have to start from scratch and you have to reinvent everything you need. Or nowadays, there's a few convenient frameworks that are developing to help manipulate semantics at a lesser cost. And skeletal semantics is one of them. The idea is that we have a very simple and very small meta language that we call Skell, in which we can define other programming languages. So you take your favorite language, like JavaScript, and you define it inside this meta language Skell. Once this is done, you have access to a toolbox that is already written, which is able to produce for free tools like interpreters, debuggers, or export towards the Coq definition files, things like that. So now onto a small example to see how it works. A few slides ago, you had the call by value lambda calculus on paper, and now you have the definition on skeletal semantics. The first thing to notice is that you can keep things unspecified in skeletal semantics. So for lambda calculus, you can say that there exist variables that we will name ident, and we do not care about the actual implementation, so we can leave it at that. You can also give specified types, like lambda terms. Once again, a lambda term is either a variable or an application or a lambda abstraction, and you can define them as algebraic data types. Same for evaluation functions, you can keep some of them abstracted. So for instance, environments are not really the centerpiece of call by value lambda calculus. Whatever the implementation is, as long as your environments can be extended and can be read, then everything is fine. So you can keep all of this abstract, either for modularity or to give a definition later. And the important part is that evaluation functions can be defined in skeletal semantics. So here we want to explain how a lambda term is evaluated inside an environment. And to do so, the definition uses this meta language. So the semantics of the language you're interested in, like lambda calculus, is defined within the syntax of the meta language. And one of the things available in the syntax of the meta language are branchings. They're a bit weird, but the idea is that branching is simply a list of all possible behaviors of an evaluation function. So here we say that this eval function has 3 possible behaviors depending on the constructor of this lambda term. These branchings can be used for non-deterministic choices, but we can also combine them with other constructors to create pattern matchings or conditional statements. Here, the way it works is that we have destructive lets, like in the third line, where we have let lambda xt equals L. And this line will behave as expected if L is a lambda abstraction, and it will block this behavior if L is not a lambda abstraction. So basically, by combining those lettings and the branching, we can have a pattern matching. And just as before, we explained that if we want to evaluate an application, we evaluate both parts, extend the environment, and compute the rest. Yeah, so this is everything that a user will need to do to define lambda calculus inside skeletal semantics, and then have access to all the tools we developed. So the syntax of this meta language is very small. That's the point. It allows us to really easily manipulate semantics. And so to define an evaluation function, you have to give a term, which is a computation that cannot progress further. So you can see it as a normal form. So either a constructor or a tuple or a function. And we also have mutually defined skeletons. So skeletons are defined with terms, terms are defined with skeletons. And skeletons correspond to computations that can go further. So they can be either application of a term to other arguments, or a Latin saying that we evaluate first S1, then do some extending of environments, and then computing S2, or the branching I presented earlier, saying that we can have a non-deterministic choice between several possible behaviors, or simply a term when you're done to return something. And functions also use patterns to be able to do pattern matching on terms. So what about the semantics of the meta-language scale? Well, we do have a semantics for the meta-language written in big step form. So it is really great. It is quite readable and useful for some proofs in Coq, but we can't do everything with a big step semantics. And the point of this work is to develop other semantics for this meta-language. And we would like notably to have abstract machines because they have finer grained definitions and more details on how steps operates. Notably, it would be great to have something executable because so far we still don't know how to execute lambda calculus even after all those definitions. And so to get abstract machine semantics out of the big step semantics we already have, there's known techniques developed by Danvy and et al. To explain how to go from big step to abstract machines without having to think about it too much. And the main two steps are CPS transform, which are about splitting calls in between premises to create continuations, and then defunctionalization to transform those continuations into objects. I'm not going to go too far into explaining the transformation, and I'm just going to skip to the result. If we apply these techniques to our big step semantics of the meta-language, we get an abstract machine for our meta-language, and it looks like this. So a bit of a summary on abstract machines. An abstract machine is a reduction system between abstract machine states. And the machine states morally represents the inner working of a virtual computer that would be evaluating something. So what you have on the left here corresponds to the state of a machine that would be computing a branching with an environment sigma and with a continuation kappa. And what the rule says is that if a computer should evaluate a branching, well, it should just take one of the branches in the branching and just focus on it and just throw everything else out. For Latins, what these rules say is that to evaluate let p equal S1 in S2, we should first focus on S1, evaluate S1, and keep in mind somewhere that there's still something left to compute. So we create a new continuation that says later on we still have to do the let p equals in S2 part and save it for later. And when this later arrives, when we get our result R from computing S1, we can depile this continuation and then do the rest. So some pattern matching to extend the environments using the variables in P and our result R, and do some pattern matchings. And then remember that we still have S to do somewhere later, so we still have to create another continuation to remember that. And when we get to it, we can just compute S finally. So it works, and unless we've messed up, it should be equivalent to the big step definition that I did not present. But we still can do something more precise because for now, this definition is non-deterministic, by which I mean that the first line, when we say that when we have a branching, we take one of the branches, we don't explicitly say how we do it. And so we can't have something, you can't have an executable semantics from here. To create a deterministic semantics, we need backtracking. And for this, we follow the same techniques as previously, but we use a more complex CPS transformation that is able to create two kinds of continuations. So once again, I'm going to just skip to the result, and we get something like this. So now every machine states has one additional parameter, which is a failure continuation, which you can see as a list of checkpoints to go back to in case something wrong appears. So now if you have a branching, you say that if there's at least one branch, you just take the first one. There's no choice involved, you just take the first one. But we don't throw out of the window the other branches. We save them in a new continuation, a failure continuation, a checkpoint that says if something goes wrong later, we can just go back to them. And for instance, if we try to evaluate an empty branching where there's no possible behaviors, we just want to backtrack. So we just focus on this failure continuation. All the rules for letting are exactly the same. We just have this additional parameter that is present everywhere, but it works exactly the same. And we have a rule for backtracking that says that if we have given up on evaluating something and we want to backtrack, we just open up the last checkpoint and go back to evaluating whatever was inside. So now we have something that is deterministic, executable, and once again, hopefully it should be equivalent to the big step semantics we had at the beginning. So now the next phase is to make sure formally that we did not mess up and that it is indeed correct, that what we wrote makes sense. And we do this in Coq. The big step semantics of the meta language was already written and defined in Coq. And so now we define the non-deterministic abstract machine from 2 slides ago and the deterministic one just above. The non-deterministic one has to be defined as a relation because it is not computable, but the deterministic one can be defined as a Coq function. And so then the certification comes to proving that the big step semantics is completely equivalent to the first abstract machine. I'm not going to go into the details of the proof because it is really a textbook proof and there's nothing weird with it. And the second part is to make sure that the deterministic version we just presented is sound with respect to, well, the non-deterministic one and by extension the big step one, in the sense that if the deterministic abstract machine finds a result, then it is a correct result. So there will be a bit of hand waving, but the main idea of the proof is that a sequence of prediction of the deterministic abstract machine always takes the first path when there's a possible branching, where there's a choice, and backtracks when something goes wrong. And so the sequence of predictions has those loops mingled in the sequence. And the point of the proof is just to notice that, to explicitly find those loops and delete them. And when you get rid of them, you can just take what's the remaining part of the path, and it is a correct path for the non-deterministic abstract machine, where you don't have to guess which branch to take. Finally, with these Coq definitions, we can go a bit further because the deterministic abstract machine is executable, and Coq definitions can be extracted to OCaml. So we have an OCaml definition of this abstract machine of the meta language. And we can use this to provide a certified interpreter to the user. So from the user perspective, the first part is always the same. You take your favorite language like JavaScript, you define it into scale, and we already had a way to transform this user definition into a Coq definition file. This definition in Coq can also be extracted to OCaml, combined with the abstract machine of the meta language to provide a certified interpreter. So at no additional cost, you can have an interpreter running this abstract machine. And the last slide is a summary of the talk, because having a meta language to define other languages can be a bit difficult to follow. So at the meta level, we already had the big step semantics of scale. And using known techniques, we created new semantics for the meta language. Since one of them is executable, we also get a certified interpreter for the meta language. On the user side of things, we already had a few tools to make use of user definitions. Notably, we already had another way to make an interpreter, but without using the meta language. So this one comes without any guarantees. And using this extraction towards the Coq definition file, we can also use it to specialize this meta interpreter to get a certified interpreter for any language, which means that now you can have a certified interpreter for any language defined in skeletal semantics. Yeah, that's about it for this presentation. So thank you very much for listening.
Thank you for a great talk. And let's give the big clap here. And there is a question. Have you actually managed to semantics one often wants to prove safety properties like progress and preservation? Sorry, I was mixed. Have you actually managed, as sanity checks for formal semantics, one often wants to prove safety properties like progress and preservation. Can the generated Coq specification be used to prove such properties?
First, do you hear me, even in Philadelphia?
Yes, we do.
Yes, okay. So proving properties like progress and preservation, yes, that's the point of extracting towards the Coq definition. We can do this with either a big step specification, semantics of the meta language, or small step one or something. We can do those kind of proofs, but it's a bit of work, but you have everything that Coq has to offer. So there's a few tactics to help deal with skeletons, but then you still have to know how to do this proof in Coq by yourself. And then the other question, maybe, because I don't.
Okay, the next question is that, have you actually managed to extract a certify interpreter for JavaScript like that? And will this replace the current ML interpreter generator from the Scale project?
Okay, so for the certified interpreter for JavaScript, not yet, but it should work soon, because I'm not sure the definition of JavaScript inside Skeletal Semantics is not yet finished, I believe. It's almost finished. There's thousands of lines of definitions, but I think it does not work completely yet. So soon, TM. And about replacing the current interpreter, no, because there's, well, this certified interpreter is an interpreter for the meta language that is specialized, which means that it is still more difficult to follow and more difficult to use for the user, because you have to know how to handle those skeletons. The current ML interpreter really creates an interpreter for your own language and gets rid of all the skeletons. So it is easier to use and it is faster because there's less overhead. So for performances, it's also, well, the certified one is slower. So it's not a replacement, it's just something aside that can be used to check some tests or to be used as a formal debugger, because that's the one where you know the result is correct, but it's slower.
I actually have a follow-up question of Dan's. So you said that you are writing down JavaScript specification inside your skeletal code, and are you targeting on the latest specification proposed last year?
I'm not sure. We started with the ECMAScript from 2 years ago, I believe. And the point of Skeletal Semantics is that then it should be easy to add new features of languages. So once this is finished, we can add new features of new JavaScript easily, theoretically. We hope so.
I'm asking this question because JavaScript language specification itself is quite big, and even writing it down in the language is going to take a lot of energy and effort. And how do you handle such a big project?
Well, first, the hard part is that JavaScript uses a lot of monads to get things in order. So to extract values and check that we have some specifications and to bypass some evaluations in certain cases, we have a lot of monads. And so first we had to develop a lot of support for monads. So the small meta language that I presented has nothing much, just branchings and lettings. So it looks like it will be difficult, but we have syntactic sugar for monads and ways to inline them and simplify computations. So definition can be really small. And we have a JavaScript definition that looks a lot like ECMAScript. If you put them side by side, the definitions really look alike.
I'd like to ask if there are any in-person questions in the hall or any other remote questions.
Any questions here in Philadelphia? It looks like no.
All right.
Okay, I think we have about 5 more minutes, but I think we can finish here if there are no more questions. And thank you so much for your interesting talk. And